In this last section of Chapter 6, we'll look at how to solve overdetermined systems. So what that means is if you try to solve ax equals b, you get no solution. And to get the best approximation, we will solve A transpose ax equals A transpose b. This system is called the normal equations to ax equals b. And the solution to A transpose AX equals A transpose B is often used with an X hat, so it's an approximation, and it is the best approximation to X. So let's use the normal equations to solve this system, AX equals B, where A is that matrix and we're given B. So I'm going to construct A transpose A first. So A transpose is 2, negative 2, 2, 1, 0, 3. And notice this is a 2 by 3, this is a 3 by 2, so our output is a 2 by 2. Multiplying out, we get 12, 8, 8, 10. I just want to point out that this matrix, A transpose A, will always be symmetric. In other words, if you fold it along the main diagonal, it'll be the same. Now let's look at A transpose B. So we have a 2 by 3 and a 3 by 1. So our output is a 2 by 1, and you get negative 22, 1. So the system I want to solve is the 12, 8, 8, 10 augment with negative 22, 1. If we use some technology to row reduce this, we will find our solution is negative 57 over 14 and 47 over 14. So my x hat, or the approximation to ax equals b, is the negative 57 fourteenths and 47 fourteenths. So I can't plug this back in to ax equals b and have it work, but it is the best approximation. So to find out how far off you are, like how close is it, you can find this quantity, the norm of b minus ax. So keep in mind, b is what you want it to equal, and ax hat is the approximate. So exercise 2 asks us to compute the error associated with the problem we just did. So we want to look at the norm of negative 5, 8, 2, that's your b, times, or minus the a times the x hat, the approximation. Now this is not something you want to do by hand. There are, of course, online tools. The one that I used is MATLAB. Octave is the free version. And I just did the norm of, and I defined b and a, and then times x hat. When I did this, I got about 0.2673. So this is the error in that x hat solution. A transpose A is often invertible, meaning that there is a unique solution, although it is possible to not have a unique solution. So let's look at this example and see what happens. So again, I'm going to find A transpose A first. Multiplying out, I get 4, 2, 2, 2, 2, 0, 2, 0, 2. Again, just thinking about checking yourself, it is symmetric across that. If you fold it right there, you get the same thing on both sides. A transpose B is 14, 4, 10. So putting them together, we want to solve the system. And if we row reduce this one, we can see that column 3 does not have a leading one, so it's free. So x3 is free. x2 is negative 3 plus x3, and x1 is 5 minus x3. So that is a description of all the least squares solutions for this system. Again, more often than not, you get a unique solution. So we often hear about the line of best fit or using least squares. I just wanted to provide a different example of how you can use least squares. According to Kepler's first law, a comet should be either elliptical, parabolic, or hyperbolic in their orbit. And the r theta represents the position in polar coordinates, and it satisfies this equation. So r is the radius, theta is your angle. B and E are both constants, and they tell you that E is between 0 and 1 for an ellipse, E equals 1 for a parabola, and this should be E greater than 1 for a hyperbola. And suppose the observations are given in this data, in this table, and I want to determine what type of orbit it is. Ultimately, what I want to do is I am given data for r and theta. The beta and the e both have exponents of 1, so they are considered linear. So we're going to solve this with linear equations. I first want to plug in the data to set up the linear equations for b and e. So using my first data point, this 0.88 theta and r is 3, I have 3 equals beta plus e times 3 cosine 0.88. I'm just going to keep doing this. Once I've plugged them all in, I'm going to actually find the value of these components. Now I have them written as 5 equations with 2 unknowns. So overdetermined because you have more equations than unknowns. I'm going to rewrite this in matrix form. So A, my x is beta e, those are the unknowns. And my right-hand side is 3, 2.3, 1.65, 1.25, and 1.01. And then the matrix A is the coefficients, so it's 1 and 1.911, 1, 1.043, 1.248, 1, negative 0.247, 1, and negative 0.544. So here's my A, my X, and my B. It's overdetermined, which means X does not exist. There is no solution. So we will solve X hat using normal equations. So I encourage you to try this. I'll write down the solution, but I encourage you to use technology to help you with that. When you solve using the normal equations, you'll get this approximation. X hat is about 1.4508 and 0.8113. So that tells me that beta is about 1.4508 and E is about 0.8113. So what they asked us for says determine the type of orbit. So because my E is between 0 and 1, that means it's an elliptical orbit. And then it says predict where the comet will be when theta equals 4.6. We started with this initial equation, so I know that r is equal to 1.4508 plus 0.8113 times r cosine theta. And it wants to know what is r when theta equals 4.6. Cosine of 4.6 is negative 0.1122. When I multiply these two together, I have r equals 1.4508 plus negative 0.091 r. Adding to the side, I get 1.091 r equals 1.4508. I get that r is about 0.752. I just want to point out that I've done a lot of approximating here, and if you're using technology, you would not, you'd use more precise answers. For example, when I created this matrix A, I would put in like 3 cosine 88 and keep more than just 3 decimal points. So keep in mind these are approximations.